because our first speaker this afternoon is Craig Chamberlain. So Craig is the head of detection science at Elastic, which I think makes his talk doubly relevant for our threat hunting summit, since he's not only involved in producing one of the most popular data platforms for hunting, but he's also going to give us some really good concrete examples of the analytics, like how to apply machine learning techniques to find evil in big chunks of data. So Craig, thanks for being here and welcome.
Sure, thanks for having me. So my name's Craig. I've been working on threat detection for threat hunting and detection for a long time, and I've been working at Elastic for almost 3 years now, working on a lot of search and query-based threat detection, but also more recently on exploring applications for machine learning-based threat detection and what we could do there. And so I wanted to show you some of the results that we found so far. So what I have is I have kind of like the greatest hits and the best results that have come out of machine learning-based threat hunting so far, in 3 general categories, some from endpoint data like process data, some from network data, and some from cloud API logs. And so I'm going to just pause video during the slides, and then I'll resume video when I finish. So in terms of why use machine learning, I think the short version is I'm not proposing that we just stop using everything else and just start using machine learning. I don't think we're there yet. I don't think anyone's really proposing that. I do think it can be a valuable additional tool in sometimes finding things that are hard to find using conventional detection technologies like search or query or behavioral alerts or other technologies. And sometimes using a machine learning tool set is useful in order to do this at scale and to do it continuously at great scale. And in order to get good results, it can be really useful to employ a machine learning framework. So the 2 questions that come up first are one, how is this different from just stack ranking and outlier detection, right? Running really large queries, either in a query language or maybe in a data analysis tool. And the other question is, how are you going to make sure that we don't trade alert fatigue for anomaly fatigue? So they're kind of interrelated. And so I won't go into this in great detail here because I could spend the whole time we have on this, but what I will just kind of sum up. And there's a really good blog post here where it goes into a much deeper dive on how we're doing this stuff. There's even a video that kind of steps you through some of the functions, which is nice. I like to kind of step through functions when I'm understanding something new. But the short version is what we do is, it's a bit like a hunter running a really large query and sifting the results looking for outliers. Where it differs is that in order to get good results, we like to do this on all of the data for all time. So we run these jobs continuously in what we call bucket intervals, which are just time intervals, usually 15 minutes, sometimes 60 minutes, depending on which gives us the best results. And then we do statistical analysis on each bucket, and then we do statistical analysis in the macro across the entire set. And then we output interesting results in the form of statistical anomalies in the data. And where it gets more complex is sometimes in order to get good results, sometimes I partition the models. So it's not just looking for a rare entity like a rare process, but sometimes a rare process for a particular host. And there are a number of other cases. And so that quickly becomes too large and too complex to try to do it in your head. So it's useful to do it programmatically, like this at great scale. In terms of how do we make sure that we don't get too much output, I've done a lot of work on that. And so what I've done is the queries that input my models are called data feeds. We call them data feed queries, and they're essentially just Elasticsearch queries. And what I've done there is in measuring signal to noise, I'll add exceptions into those queries to try to remove potential pollution from the models. So like a Jenkins server, for example, can create a large number of rare processes, and there are a number of other things that can. So it can exclude those from the model at ingest time, and that helps to increase the quality of the results. And then what happens is the models compute, they output anomalies, and each anomaly has a score between 0 and 100 in terms of how interesting it is or how anomalous it is. And so I typically take the top 50 to 75% of the results and turn those into alerts by default. And I find that that works well, and that produces a good number of interesting alerts, but not a flood of alerts, because we don't want to have a flood of alerts or anomalies. We don't have a flood of alerts in any class. The other thing we can do is, I've had really good results doing sort of multivariate correlation where we're joining machine learning alerts with conventional search query-based alerts, behavioral alerts, threat intel matches, malware detections, and other kinds. I find that when two or more of these detection pipelines agree that something is suspicious, then the confidence tends to go way up. And so I've also developed something experimental for clustering alerts by risk score. And that's something that I can share in the chat after the talk. So let's dive right into some examples of some things that have actually been found with machine learning. So my first set of examples are for endpoint data. And so in the endpoint data, I have 64 of these jobs now that are running in production, and a good number of them are running on process data, process execution data from endpoints. And some of them are looking for things like rare processes. Some of them are looking for rare path process creation, like parent-child relationships. There's another one that's pretty good at finding obfuscated PowerShell script block content. And the reason that there is more than one flavor of some of these, like rare process, there's a job for rare process for a particular host and rare process across the entire host population. And the reason is that each one excels at finding different things. So for example, and it can also help with prioritization. Like for example, there often are server application types out there that will manifest rare processes occasionally, and that's normal. Like some finance applications will run a process that only manifests once per quarter or once per month or once per quarter, something like that. And that could be uninteresting if it's a finance server. If it's a rare process on something like a domain controller or an Exchange server or an AD DNS server, those, at least plain vanilla versions of those, they tend to have less behavioral variance and spread. So finding a rare process on one of those can be more interesting and often can be higher priority too. So back in May, we were working on detection methods for a Nobelium campaign. This is a group that's been active for a while, but in May, we had a high priority project to make sure that we were detecting this latest campaign. And what I found is that we're able to detect this using some of the unsupervised ML jobs and alerts without any prior knowledge of what the IOCs or the behaviors look like. And so in this case, what I got a couple of different anomalies-based detections on this. One was that there was activity in an unusual working directory, because in a well-regulated or in a Windows environment with heavy security policies, sometimes it's unusual for users to be just running things from their profile directories. Not always, but sometimes it is. Sometimes it's unusual for users to be running things from strange locations. And so rare path was one detection. And the other one was a job that found a network activity from an unusual process name connected to the network socket. Basically an unusual process name talking on the network. And that was actually that job is one that some of my threat hunting users have suggested, and that one turns out performs pretty well. So in that case, we found it was the DLL loader was running. It was actually this particular campaign was using a DLL, so this DLL was loading in. We actually got both of the C2 IOCs that we had at the time back in May actually showed up here. So that was cool. As far as other directions, other possibilities here, there are other possibilities because there was a very strange DLL name in the sample here that when we detonated it. I think anomalous DLL activity, I think, is also probably fruitful. It's going to take a little bit more work because DLL loads there's a huge number of them, as you might imagine, and DLL names are going to tend to have more more cardinality, which means uniqueness, and there's going to be more of them with more unique names, and they're going to have more variance and more variability, and that they're going to be there's going to be much more variety of DLLs both across the entire host fleet and a particular host. And so that presents a cardinality problem. But I do think that we can likely potentially detect things like this by looking for anomalous DLLs as well. The other possibility is the beaconing, of course. Beaconing is a good way to find things early, and we're working on something for beaconing at the moment. And in a beaconing prototype, I found we actually did pick up both of those destination IPs and classified them as beaconing as well. But that's forthcoming research. So in the network realm, I'm going to show you kind of like my best examples in all three categories. So endpoint, network, and cloud. So in the network realm, one of the things I like to do, especially if there's a large set of network data that's being ingested and processed, but maybe it hasn't really been hunted yet or analyzed in great detail. One of the things that I like to do first is to plot it geographically, because it can be done. You can do this and digest the results in a relatively short time. And it's a simple technique, but I found that this technique has produced a half a dozen or so really big cases that were really fairly significant in the course of my career. And so it's just one useful technique that I like to employ, not for network data, also for authentication data. But in this case, my examples are in network data. So these jobs are looking for unusual destination countries, and they're looking for unusual spikes in network traffic and network denies. And the first one is partition. It's looking for an unusual spike in traffic to a particular country. And so these are sort of relative. So what's great about these is that we're not giving it a number and say, show me when the network volume goes above 10,000 flows per hour or something. We're not giving it a static number. It's much more dynamic. So it'll find peaks and troughs that are not just peaks and troughs, but peaks and troughs that are unusual for the network where this is taking place. And so this is sort of similar to what we could do. Like, you can find this stuff by visualizing network data. And I like to visualize stuff because you can often, if there's something going on, you can often see it in a network viz, and you can see, find unusual peaks and troughs. So in this case, this was a case where I was actually beta testing these network anomaly detection jobs, and I actually found a malware instance where it was getting stopped at a border firewall, but it was actually trying to get out and connect to its C2. And the C2 was in a destination country that was unusual, didn't have a business relationship. And so I said, hey, is this something? And it turned out it was. And so this was a good find. We also got a couple of hits actually for an unusual destination country. And the fact that it was getting denied at a border firewall gave a big spike in firewall denies. Not just a spike in firewall denies, but it was a spike in firewall denies that was very, it was unusually large relative to what normal day-to-day, week-to-week looks like. And so, so we get a few different detections there. So that was great. Now, of course, geographic detection, of course, is not by any means a silver bullet, because we can evade geographic detection by just not being a geographic anomaly, right? Just locate C2 in the same country as the implanter or the victim, or in a country that looks normally in terms of business relationships. And so in this case, so back in December, one of the jobs detected Sunburst C2. And the way we did it was not a geographic anomaly. It was actually a job that looks for DNS tunneling, which is what I did is I adapted a technique that some of my Zeek user friends like to use, looking for a really, really high relationship between parent and child domain names and DNS events. And so I adapted that into a machine learning job, and I found that this actually found, because in this case, there was a DGA algorithm being employed, a domain generation algorithm. There was a really, really large number of child domains for one parent domain, much, much larger than anything that had manifested before on this network. And so we're able to detect that behaviorally, even though at this point, back in December, Sunburst was becoming, I think, a known campaign. But what's great about this is that this is something where we could have detected sunburst potentially earlier than December, even when the sunburst IOCs weren't quite out yet and we didn't quite know what to look for. It's a good example of potentially finding something interesting, even though we don't know what we're looking for. So in the cloud domain, I've got a few examples. And this is a case where, what I'd say about cloud is, this is a case where some of these techniques, doing anomaly detection on cloud API logs, might actually be even more useful in the cloud domain, and possibly even given the results in what we can do here, I think that machine learning anomaly detection could possibly even be kind of a go-to detection technology in the cloud space. And the reason for that is because in the cloud world, we have, it looks different, right? So we have virtual machines and virtual servers and containers that run operating systems, and they look like virtual servers, and we can instrument them with endpoints, we can measure network flow logs, and we can do conventional detection and threat hunting there just pretty much most of the time. But then there's this whole other world of pure services that don't traverse the virtual networks. And you can reach them from the virtual networks that your virtual servers are on, but they don't necessarily traverse the virtual networks that you can observe via virtual intrusion detection, virtual firewalls, or flow logs, or some other means. They're reachable from basically anywhere. And so, we can't monitor the control plane networks in public clouds because they're multi-tenant. Only the provider can do that. So there's all this service and API activity going on that really can't be observed with conventional either endpoint or EDR-like tools or next-gen firewalls or network tools. So that's one aspect of it. The other aspect of it is that most of the time, not always, but it's often the case in the cloud incident world, we're talking about credentialed access. We're very often looking at cases of credentialed access where somebody has obtained a set of valid credentials and they're just impersonating a user and just persisting in the control plane and using services in the control plane to achieve their objectives. And there are a lot of services in there. There actually is there's a section in the attack matrix for cloud techniques, and there are a number of them now. The overwhelming majority of it is going to relate to credentialed access. And so the difference in a legitimate user engaged in perfectly normal activity and a hijacked user context engaged in suspicious activity is often a matter of nuance. So what does that mean? So in terms of examples, there's a few good examples here. So in the public record, there's a couple of case studies out there. One of them is from 2016, where and this was an incident and an intrusion set that was not just cloud. There were many dimensions to this, but there was a significant and kind of interesting cloud dimension to this. Because the exfil method was kind of novel and new at the time. It was something that I hadn't thought of, and I'm not sure that many people had thought about doing this, where once they got access to the cloud account, they actually used supported functionality to share snapshots of virtual cloud servers and basically just share those snapshots back to their cloud account that they controlled in order to just kind of forklift the data back to an account under their control. And so that was interesting because that was something new. And this is a case where now, of course, we could alert on something like this if we want to, because when a snapshot is shared, like most operations in the cloud APIs will leave an audit trail in the audit logs. And so this is what it looks like when somebody shares a snapshot. And this is one of the few examples where you'll actually see somebody else's account number, because you'll see the account number it was shared with, because you kind of need that in order to try to figure, because you need to know, is this my account? If it's not my account, it's someone else, then we need to find out what's going on. So we could alert on that with a search rule. The issue is that if we do that, if sharing snapshots is something that is used normally by development teams working across different accounts, and then we generate a burst of alerts on those, then it's just going to create create more trouble than it's worth. I strive to try very hard not to alert on normal activity, or try as little as possible on normal activity, because something like that would just create the ratio of noise to signal could quickly become so large that chances are an alert like that would be disabled. So the other example is, the next example is, there's another case study out there where somebody actually bounced through a web application firewall or a WAF service. They figured out they're able to pivot through this WAF service in order to get to what's called the metadata service in a cloud account. And the metadata service is it's a kind of an infrastructure service running in the cloud accounts, where a virtual machine or virtual server can ask questions about itself and get answers. And sometimes virtual servers can request temporary credentials from the metadata service, or credentials or secrets in order to authenticate to different services, depending on what roles they have assigned to them. And so what happened is somebody's able to bounce through a WAF service and then interrogate the metadata service from a virtual server and grab a credential out of the metadata service. And then that credential worked from outside the cloud, so that they were able to log in, they were able to access that cloud account coming from either from Tor or VPN or someplace, or possibly both, and then gain access to bulk data in a storage service called S3. So for these cases, I've made 5 machine learning jobs so far for cloud audit data. So, and these are they're looking for the kinds of nuances that we need to find in these kinds of credentialed access attacks. So we're looking for unusual requests by a particular cloud user, we're looking for unusual geography. So a cloud transaction request coming from a very unusual city or country. And the reason is because we're looking for both of those ingredients that we saw previously. So we saw a user context coming from an unusual location, and a user context calling unusual methods, calling a method like list buckets that it had not called before. Error codes, so outliers and spikes in error messages are also interesting, because I find that if somebody's persisting, if somebody has a shell on a virtual server and they're running a post-exploitation framework like Parquet or Bark in order to enumerate privileges, in order to either pivot into the control plane or possibly move laterally amongst virtual servers, as they do that, it will tend to create a burst of errors and access or authentication denied messages. And so that can also be interesting, kind of an indicator that something's going on. Rare error, interesting enough, has observability use cases, because we find that a rare error sometimes will predict an imminent service failure, that a cloud service is going to degrade or break down within the next few minutes. So that's used sometimes by some of my operations or SRE users as well. So what these give us is, let's take the list buckets example. In the second case study, the threat actor persisting with the compromised credentials was using the list buckets command in order to enumerate basically data stores called buckets. Now, this method, even in a small cloud account, the odds are this method is used way too often for us to try to alert on it. In a medium-sized environment, you can easily do tens of thousands of calls to this message per month. But even if we could, just alerting on the method is not that useful. What we need to know is we need to find not just innocent, ordinary user activity calling that method. We need to find malicious or suspicious user activity in the case of credentialed access, or a user context who's calling that method who shouldn't be. And so the way I've done this, a couple of different ways, is one of the 5 jobs that you saw is a partition job. We're looking for a rare request or method for a particular user. So like in this case, this is a case where I'm actually calling the list buckets method, which is something that I don't ordinarily have cause to do. And so that output an anomaly. So we basically were able to calculate the fact that because this user context has not called this method before, and it's extremely rare, we can generate an anomaly on that, and then we can go and ask the user, in this case me, why I'm calling that method. Similar for other things, so especially for things like privileged methods, like security groups, identity and access management methods, sensitive methods, usually those are not being called by random users. Now, developers could be in there doing break fix, they could be troubleshooting something, certainly. But whenever a sensitive method is coming from an unusual user context, it could be interesting. Same thing here. So in this case, I'm calling the the share snapshot method, which is something that I don't normally do and I have no reason to do. So there's our detection example from the first case study. Another one is run instances. So many cloud accounts are highly automated or they're controlled by automation. And not all, but some are. And so it may be unusual for a user to log in and interactively start virtual machines. Because one reason to do that is if you want to persist in a cloud account, if you want a virtual server for various reasons, one way to make sure that you don't have a lot of alerts coming off is to just go start a virtual machine by hand and make sure that it doesn't run any of the normal security stack that's going to send data, telemetry, and alerts to the SOC. And so that's often useful to look for. More privileged methods. So things like some of the assumed role methods have featured in a number of threat models and scenarios. Those are often should not be coming from those. Now, in a global enterprise, they will come from many different geographies, but most of the time they shouldn't be coming from unless you've got a change in workflow, they shouldn't normally be showing up from geolocations that they've never sourced from before. Same thing for login. So this is just a console login into the control plane. From an unusual country, we can do the same thing for authentication events. I've had good results plotting geographic anomalies or source anomalies for login events, authentication events. And then finally, for the metadata service, because the metadata service was an ingredient in the second case study, the metadata service is like I described. It's basically an information service where a virtual server can ask questions about itself, and it's mostly used programmatically, and it's used a lot. And so the cloud management agents will call this service. Automation that's developed and instrumented by cloud users will call this service. Lots of things call this service all day long. And so there's way too many events to think about alerting on calls to the metadata service. We can look for unusual processes calling the metadata service and unusual user contexts. So like in this case, we've got a user hitting the metadata service just using curl, which is unusual for this environment because they're in a highly automated, regulated cloud environment. There aren't normally a lot of users in there running things by hand. And then same thing, here we've got an unusual user context calling the metadata service. So this is me. Now, this is not necessarily a critical detection, right? Because this could be an SRE who's troubleshooting something in prod. It could be a developer doing break fix. If it's not, though, then it's a good question, and it can be interesting to know why is a human user interrogating the metadata service by hand. So in terms of future directions in the road ahead, so I have more than 700 of these in development at present, so you can expect to see more of these in the future. I've done work on, in addition to the unsupervised jobs, I've done a lot of work on detecting lull-bin activity and some other hard to find things using some supervised models. Doing work on clustering and multivariate correlation of machine learning and unconventional alerts using risk score clustering. That's all available actually, and I can share that. I'll share all this in the chat after the talk. That is my talk. I think I'm just about on time.
You are exactly on time. Thank you, Craig. We might have time for, there's a bunch of questions in the Slack. I think we have time maybe for one of them. I'll just pick one at semi-random. One of the questions here is about the availability of the specific examples that you were showing. So like it says, are these available for the community, or is it just a showcase of the possibilities? And the follow-up is, if it's, what do you recommend for resources to learn to make things like that?
Sure. The short version is it's a mix. So some of this, like the risk score clustering and the beaconing detection that we're working on, some of that is going to be just open source, and at least as of this moment, it's going to be just open source and freely available. Just anybody can run it in the Elastic Stack. Some of the unsupervised and supervised machine learning models, they're not part of the free version of the Elastic Stack, but if you want to try them out, there is a 14-day trial, but I won't go into that here. But if somebody wants to try them out, I know that 14 days is not much time. It is possible to do a longer trial, like up to a month or two, if you need to. So I can help with that offline.
Great. Well, thanks, Craig. Really appreciate it. You have a number of other questions waiting you in your hallway Slack channel. So hopefully you'll have time to drop by and answer some of those.
Definitely. Thanks very much.